Now the phase diagram for water. Let me first give you the diagram, then we'll discuss. Yes. So look at this. Solid, liquid, and the vapor. Okay. Okay. This is the triple point. This is the critical point. Coming to the critical point of water. It is 374 degrees centigrade. Nothing but TC, critical temperature. Now the pressure corresponding to this is critical pressure, and of course the critical pressure is 218 atmospheres. Now coming to the triple point, in case of water, the triple point can be given as 0.01 or specifically 0.0098 degrees centigrade. Coming to the pressure at the triple point, it is 0.006 atmospheres, or in pascals, it can be given as 611 pascals. Now coming to the boiling point, say this is the boiling point of water, 100 degrees. Then we know that the pressure at the boiling point is Of course, 1 atmosphere, right? Nothing but 101,325 Pascal. Then, just before the critical point is the melting point of water. Okay. Now, see, it actually resembles the phase diagram of a pure substance, except in one simple point, one simple case. Only difference that we find in this, see, earlier, if you remember, this line was actually this way, right? But now it is sloped backward, isn't it? It has actually got backward rather than going in the forward direction, as in case of the pure substance. But why? And what does that indicate? If we see what has happened, see from this point to this point, there is increase in pressure, right? Pressure is increased, no doubt. But at the same time, look at the temperature. The temperature is decreased if you observe the two values. It has sloped backward, and if you observe the pressure at a high pressure, the melting point is decreased. The melting point was here earlier, but now it has come here. Pressure was actually here, but now when pressure is increased to this, melting point is decreased. This is what we learn from the curve that has sloped backward. Okay, let us discuss in detail about that. See, this as such indicates that in case of water, melting point gets lower, becomes less at high pressure, right? Melting point is decreased when pressure is increased. Now the reason. Why so? Now for that, let us consider this equilibrium. Ice water. We know that the density of ice is less, whereas that of water is more. Okay. Now, what if pressure is applied on this equilibrium according to Le Chatelier principle? In this case, when density is more, volume will be less, of course. Now, when pressure is applied on this equilibrium, obviously the equilibrium shifts in that direction where there is decrease in volume. I mean, more water is formed and equilibrium shifts in the forward direction, isn't it? Liquid water is produced, equilibrium shifts forward. When pressure is applied, according to Le Chatelier principle, equilibrium shifts forward. That means liquid water is produced. Okay, that means at high pressure, liquid water is produced. Now let us discuss or let us take the same thing in backward direction. Let us take the same thing in backward direction. I mean, if suppose we want to make the liquid water freeze, liquid water to freeze at this high temperature. See, when you try to freeze the liquid water at this high temperature, the only way by which you can do that is by reducing the temperature. By reducing the temperature, that means at a lower temperature when you are at high pressure. Okay. Let me give that. To make liquid water freeze, again at this high pressure, temperature has to be reduced. See the two things. You are under high pressure conditions, and in order to freeze, temperature has to be lower. That is the reason why you got a curve that has sloped backward. Okay. Therefore, Simply it can be given as higher pressure, lower melting point. Okay. Now let us take the phase diagram of carbon dioxide. I have one very important point to say in this. Okay, look at this. See, the interesting point to be observed here is the triple point which is much above the atmospheric pressure. Now, this is what we have to consider. Much above the atmospheric pressure. What does that indicate? See, it indicates that you cannot form a liquid at a pressure less than this. Of course, that is very clear. This is the first important point here. Now, one more important point is, look at this. You know, CO2 will sublime at 1 atmosphere. I mean, if we consider the atmospheric pressure, CO2 sublimes at 1 atmospheric pressure and minus 78 degrees centigrade. Okay. Now this is in fact a very interesting point. It is because of this property we say this solid CO2 as a dry ice. It is called solid carbon dioxide or say dry ice because it does not melt. It does not melt into a liquid when heated. It changes directly into the gas, which is very clear from this. Solid is directly becoming vapor, means it is undergoing sublimation. Okay. So this dry ice is manufactured by compressing and cooling the gaseous carbon dioxide. Okay. So it is because there is no liquid form obtained during the heating of this carbon dioxide. It is generally called, the solid carbon dioxide is called dry ice. Okay. Solid CO2 is called dry ice because it does not melt into a liquid. When heated. Instead, it changes directly into a gas. That means undergoes sublimation. Okay. This is very important.